Picture this. It's like 2 in the morning. You're lying in bed, and that incredibly spicy, heavy dinner you had is just coming back to haunt you with terrible burning heartburn.
Oh, yeah, we have all been there.
Right. Or maybe you're waking up after a brutal workout and, every muscle fiber in your legs is just screaming. We always tend to look at the body as a binary system.
Yeah, like you are either perfectly healthy or something is completely broken.
Exactly. You snap a bone, the x-ray shows a jagged line, and boom, there's the injury. But what is actually happening in the shadows? What is occurring deep inside your tissue before things break down?
And that is the crucial distinction to make. We are just so conditioned to look for the disease, or the failure or the irreversible damage.
Right.
But between perfectly healthy and permanently injured, there is a massive, highly active biological landscape. When your cells are stressed by a harsh environment, whether that is intense physical labor or being immobilized in a hospital bed or fighting off a daily bath of stomach acid, they do not just instantly surrender and die.
They enter a kind of protective middle ground.
Exactly, a middle ground.
Well, today's deep dive is venturing straight into that landscape. We are unpacking the fascinating world of cellular adaptation in pathophysiology.
It is such an incredible topic.
It really is. And to do this, we have pulled together an amazing stack of sources for you. We're looking at foundational texts of medical pathology, some genuinely wild historical studies, and cutting-edge molecular biology research.
Really giving you the full picture.
Yep. Our mission is to figure out exactly how your cells actively reprogram themselves to survive. So what does it actually mean for a cell to be in this middle zone?
Well, it means the cell is actively shifting its own baseline. Cellular adaptation is a protective, reversible, pre-injury state.
So it's not injured yet.
Right, not injured. The cell senses that the demands of its environment have changed, and it alters its gene expression and its physical structure to find a new, stable equilibrium.
It just adjusts.
Yeah, the key concept here is survival. The cell is no longer what we would call normal, but it is definitely not injured. It is adapted.
And if you remove the stress?
If you remove whatever is stressing it out, that cell can usually just revert right back to its original state.
Wow.
It is only when the stress becomes, overwhelmingly severe or lasts for far too long that the cell crosses the line into actual injury.
It's the body's ultimate survival strategy. But before we explore the incredible mechanics of how cells actually pull off these shape-shifting maneuvers, I want to look at how we even know this.
Oh, the history is fascinating.
Because when you look at the history of medicine, we did not always understand that cells were the main characters. For centuries, the entire medical field was looking in the completely wrong direction.
They really were. They were looking at the macroscopic level or a completely abstract concept.
Like the four humors, right?
Exactly. For centuries, you had the humoral theory, where physicians believed disease was caused by an imbalance of bodily fluids, like bile or phlegm.
Which is wild to think about now.
It is. And then by the early 19th century, anatomists started pointing at whole organs or tissues. They would look at a swollen liver and simply declare, well, the tissue is diseased.
But they weren't zooming in enough.
Right. They lacked the conceptual framework to look deeper. They were treating the forest without realizing it was made of individual trees. That entire paradigm shattered in 1858 thanks to Rudolf Virchow.
Okay, let's unpack this, because Virchow's shift is, honestly, one of the biggest leaps in human understanding.
Absolutely. He published a seminal work called Cellular Pathology, and in it, he established a groundbreaking principle omnis cellula e cellula.
Meaning all cells arise from cells.
Yes. Virchow essentially relocated the entire seat of disease. He proved that illness did not originate in mystical fluids or general tissue unhappiness. It originated down at the microscopic level, inside the individual cell.
It is like a group of mechanics trying to fix a sputtering car for decades by arguing that the car just has, bad vibes, or that the engine block is generally cursed.
Right, exactly.
And then Virchow finally shows up with a magnifying glass and says, no, stop looking at the whole car. Look right here. It is this one specific worn-out spark plug.
That is a perfect analogy. By zooming all the way in, he allowed future pathologists to ask a brand new question. What does a single cell do when it is under pressure, but not yet dying?
And that changed everything.
It built the entire foundation of modern pathology. By the mid-20th century, especially with influential medical texts grouping these observations together, pathologists realized that a pregnant uterus growing larger and a broken leg shrinking in a cast were actually expressions of the exact same microscopic biological principle.
Now, I do want to make sure we don't confuse our listeners,
Yeah.
because there is another famous scientific theory about stress from around the same time.
Yes.
Yeah, I'm thinking of Hans Sly and his stress response theories in the 1930s, because that sounds incredibly similar.
They are related intuitions, but they operate on completely different scales. It is vital not to conflate them.
Okay, how so?
Well, Hans Sly introduced the general adaptation syndrome in 1936, but Sly was describing an organism-level response.
Like the whole body.
Right, he was talking about how your whole body reacts to a threat, the rush of hormones, the activation of the hyperthalamic pituitary adrenal axis, the endocrine system flooding your blood with cortisol.
Classic fight or flight kind of stress.
Exactly. But Virchow's legacy, which is the focus of our deep dive today, is strictly cellular. It is not about a whole-body hormone rush. It is about a single microscopic cell remodeling its own living room to survive a flood.
A single cell trying to survive its immediate neighborhood.
I love
That. So let's talk about the survival strategies. Let's say the demand on a cell's neighborhood suddenly skyrockets. What are the actual biological options on the table?
Assuming the cell has the biological capability, it essentially has two main strategies for dealing with increased workload. Strategy one is to multiply. This is called hyperplasia.
Okay, hyperplasia.
Right. So if you have 10 cells doing a job, and the job suddenly gets twice as hard, the tissue divides and makes 20 cells. You distribute the load.
Strength in numbers.
Precisely. Strategy two is to build a bigger, stronger cell. This is called hypertrophy.
Hypertrophy, got it.
You keep the same 10 cells, but each individual cell bulks up, synthesizes more structural proteins, and becomes a heavy lifter.
Do they ever do both?
They do. Sometimes tissues do both simultaneously. Going back to the pregnant uterus, the smooth muscle cells undergo both hyperplasia, increasing their numbers, and hypertrophy, drastically increasing their size to accommodate the growing fetus.
But not all cells get to choose between multiplying and bulking up, right?
Yeah.
Some cells are locked into just one strategy.
Yes, and that is a massive point in pathophysiology. There is a strict rule regarding what we call postmitotic or terminally differentiated cells.
Meaning they're done dividing?
Right. These are highly specialized cells that, according to standard textbook dogma, have permanently lost their ability to divide.
Like which ones?
The classic examples are the neurons in your brain and your cardiac myocytes, your heart muscle cells. Because they supposedly cannot undergo cell division, hyperplasia is entirely off the table.
They can't just make more themselves.
Exactly. Their only possible response to increased demand is hypertrophy. They simply have to get bigger.
See, I love reading a good absolute rule in a medical textbook because science almost always finds a way to break it.
Oh, absolutely.
The sources say heart cells cannot divide, full stop. But then we get to this 2009 study by Olaf Bergman and Jonas Friesen, and it is genuinely mind-blowing.
It really is.
They actually challenged that absolute rule. And to prove it, they used, of all things, the Cold War.
It is an incredibly ingenious piece of molecular biology.
Right. So in the 1950s and 60s, the global superpowers were conducting above-ground nuclear weapons testing.
Which is terrifying, but yes.
Yeah, and those explosions released a massive pulse of a radioactive isotope, carbon-14, right into the Earth's atmosphere. That carbon-14 filtered into the plants, then into our food supply, and eventually it was incorporated into the DNA of any human cell that happened to be dividing and replicating its DNA at that time.
The nuclear testing inadvertently created a global biological timestamp across the entire human population.
So Bergman and Friesen took advantage of that. They looked at the DNA of human heart muscle cells from people born before and after the nuclear test ban era.
Such a clever approach.
And by measuring the residual carbon-14 levels trapped in the DNA, they proved that human cardiomyocytes actually do turn over. They do divide.
The number wasn't zero.
Right. It is just remarkably slow. When you are 25 years old, about 1% of your heart cells turn over per year, and that drops to about 0.3% per year by the time you reach 75.
It forces us to remember that biological rules are often just very close approximations. However, we do need to ground this discovery in clinical reality.
Fair enough, yeah.
It is fascinating that the division rate is not strictly zero, but 1% turnover a year is entirely too slow to offer any meaningful clinical regeneration.
So it won't heal you.
No. If a patient suffers a myocardial infarction, a heart attack, and loses a significant portion of their heart muscle, that microscopic turnover rate will not save them. Clinically speaking, hypertrophy overwhelmingly dominates the heart's response to stress.
Which brings up a really crucial point. If getting bigger, hypertrophy is the heart's main natural response to stress, is a bigger heart automatically a healthier heart?
If we connect this to the bigger picture, the answer is a definitive no.
Really?
The exact same anatomical word hypertrophy can describe two radically different clinical trajectories. You have physiologic hypertrophy and pathologic hypertrophy. And the difference comes down to the microscopic signaling pathways the cell uses to grow.
Walk me through those pathways, because just saying the cell gets bigger feels like it's missing the actual mechanism. How does a cell actually bulk up the right way versus the wrong way?
Let's start with the good growth physiologic hypertrophy. Think of an endurance athlete. Their heart is constantly pumping against elevated resistance during training.
Right.
The heart cells adapt by enlarging, creating what we call athlete's heart. At the molecular level, the mechanical stretch of exercise triggers a specific signaling cascade, heavily driven by the IGF-1 pathway.
That's insulin-like growth factor.
Yes. This pathway is highly organized. It tells the cell to synthesize new contractile units called sarcomeres and add them in a balanced way. The chamber of the heart actually enlarges, the walls thicken proportionally, and the heart remains flexible and highly efficient.
Okay, so the IGF-1 pathway is kind of like hiring a master contractor to expand your house. They add a beautiful new sunroom, they reinforce the foundation, and make the whole house more functional. What happens in the bad growth?
In pathologic hypertrophy, the stress isn't a temporary workout. It is a chronic, relentless strain, like untreated high blood pressure.
The heart never gets a break.
Exactly. The heart is constantly forcing blood against a massive amount of resistance in the arteries. This chronic strain causes an influx of calcium into the cells, which activates a completely different stress pathway called the calcineurin NF pathway.
And what does calcineurin do differently than our master contractor?
Calcineurin tells the cell to panic. It activates transcription factors that turn on fetal genes.
Wait, fetal genes?
Yeah, genes the heart hasn't used since before you were born. Instead of organized proportional growth, this pathway forces the cell to hastily stack new sarcomeres in parallel.
Oh, I see.
The walls of the heart become incredibly thick, but the chamber itself shrinks. The tissue becomes stiff and fibrotic. It gets bulkier, but it becomes terrible at actually relaxing and filling with blood.
Sounds awful.
It is a massive risk factor for heart failure and arrhythmias.
So it is less like building a sunroom and more like boarding up all the windows and pouring 3 feet of solid concrete against the walls? The house is technically bigger and heavier, but you definitely don't want to live in it.
That is exactly it.
That difference in pathways completely explains another huge issue in the sources, which is anabolic androgenic steroids.
Yes. A textbook example of how to profoundly damage your body's adaptive machinery.
Right, because when people abuse synthetic hormones to force their skeletal and cardiac muscles to bulk up, they are hijacking these systems. They are driving growth through superphysiologic hormonal signaling, entirely bypassing genuine mechanical demand.
It's all fake signals.
Yeah. On the outside, it mimics physiologic adaptation. The muscles look huge. But internally, the heart is undergoing that adverse fibrotic remodeling. By flooding the system with synthetic signals, you are essentially forcing the heart to use the panic pathway.
And that gray area between healthy and unhealthy growth is actually why sports cardiology is an entire subspecialty today.
Oh, really?
Yeah. Cardiologists debate whether extreme athletic training can eventually push a healthy heart over the edge into pathology. Furthermore, they are trained to look at echocardiograms and distinguish a heavily adapted, healthy athlete's heart from deadly genetic diseases like hypertrophic cardiomyopathy.
Wait, is hypertrophic cardiomyopathy and adaptation gone wrong?
No, and that is a vital distinction to make. Hypertrophic cardiomyopathy is a genetic mutation in the proteins of the heart muscle itself.
So it's not from stress?
Correct. It is not an adaptation to an external stressor. But on an ultrasound, it looks very similar to an enlarged, adapted heart. Misdiagnosing a deadly genetic condition as a benign athlete's adaptation is actually one of the leading causes of sudden cardiac death in young athletes.
Wow.
The visual result looks the same, but the underlying molecular mechanism is entirely different.
Upsizing is clearly a complex, dangerous game. So let's flip the scenario. If cells bulk up when demand increases, what happens when the demand vanishes completely?
The cells shrink. This is the third classical adaptation atrophy, but we need to define this carefully because atrophy is not simply a synonym for aging or wasting away.
It's not just getting old.
Right. It is a highly active, regulated process triggered by a loss of mechanical load, a loss of blood supply, which we call ischemia, or a loss of nerve stimulation.
Active downsizing. Our sources brought up an incredible example of this with NASA spaceflight and bed rest studies.
Yes, the microgravity studies.
When astronauts enter microgravity, they lose the constant gravitational resistance on their postural muscles. There is no load. And the adaptation is shockingly aggressive.
It happens so fast.
Right. Even with in-flight exercise protocols, astronauts can lose significant calf muscle mass and strength within just 1 to 2 weeks.
That is atrophy in its purest form. There is no disease present in those astronauts. The muscle cell simply realizes that maintaining massive amounts of contractile protein is a huge waste of metabolic energy if there is no gravity to fight against.
But how does a cell actually shrink? It can't just deflate like a balloon. What is the mechanism for tearing down all that protein?
The cell executes a controlled self-eating process called autophagy, paired with the ubiquitin proteasome pathway.
The ubiquitin proteasome pathway.
Yeah. When the mechanical load disappears, the cell produces highly specific enzymes called ubiquitin ligases. The most famous ones in muscle are atrogen-1 and MERF1.
Okay, let's slow down and explain what those enzymes actually do, because ubiquitin proteasome pathway is quite a mouthful.
Fair enough. Think of ubiquitin as a chemical sticky note that says destroy. The enzymes atrogen-1 and MERF1 act like cellular taggers.
Okay.
They identify the unused structural muscle proteins and physically attach that ubiquitin sticky note to them. Once a protein has that tag, it is recognized by the proteasome.
What's the proteasome?
The proteasome is essentially a microscopic cellular wood chipper. It pulls the tagged protein inside and shreds it down into basic amino acids, which the cell can then recycle.
I love that. It is like a corporation liquidating unused factory equipment when sales drop. They don't just abandon the factory and let the machines rust.
Yes, now it's very deliberate.
They actively send a manager, the ubiquitin ligase, to put a red tag on specific machines. Then the demolition crew, the proteasome, comes in, dismantles only the tagged machines, and sells the scrap metal. It is incredibly organized.
That organization is what separates atrophy from necrosis. Necrosis is messy, uncontrolled cell death caused by severe injury, where the cell just ruptures and spills its contents, causing inflammation. In atrophy, the cell is still perfectly viable. It has just actively shrunk its footprint to survive on fewer resources.
Okay, so we have seen cells upsize, multiply, and shrink. Here's where it gets really interesting. What happens when the stress is not about workload at all? What if the stress is a chronic, toxic, chemical irritation? A cell can't just bulk up to fight off a chemical burn.
In that scenario, the cell changes its identity entirely. This is our fourth major adaptation, metaplasia.
Metaplasia.
This occurs when one fully differentiated mature cell type is entirely replaced by a different cell type that is better equipped to handle the harsh new environment.
The ultimate shapeshifters. The classic textbook example of this is Barrett's esophagus, which is seen in patients suffering from severe chronic acid reflux, or GERD.
To understand metaplasia, you have to look at what is normal. The normal lining of your lower esophagus is made of delicate squamous cells.
Squamous cells?
Yes. They are flat and smooth, perfectly designed to let food slide down into the stomach. But they are absolutely not designed to endure a daily, chronic bath of hydrochloric acid and bile backing up from the stomach.
So the acid just burns them away.
Over and over again. Eventually, the stem cells that regenerate the esophageal lining realize that the delicate squamous cells cannot survive, so they reprogram themselves.
They just switch it up.
Exactly. Instead of generating new squamous cells, the stem cells start producing a tougher, columnar, intestinal-type tissue. That new acid-resistant lining is Barrett's esophagus. The tissue literally transformed into something resembling the intestine to survive the acid.
It builds chemical armor. And the sources highlight another major example of this, which is the smoker's cough.
Another perfect example.
The normal airway is lined with tall columnar cells covered in tiny hair-like structures called cilia. Those cilia act like microscopic brooms, constantly sweeping mucus and trapped debris up and out of your lungs.
But those delicate ciliated cells are destroyed by the chronic toxic heat and chemicals of cigarette smoke. To survive, the stem cells in the respiratory tract undergo metaplasia. They stop making the ciliated cells and replace them with rugged, layered squamous cells. It is the exact reverse of what happens in the esophagus.
So the respiratory tract builds armor to survive the smoke. But here's the catch. The new armor doesn't have brooms. The squamous cells have no cilia.
Not at all.
So all the mucus just sits in the lungs, pooling up. That is exactly why chronic smokers develop that deep hacking cough. The metaplasia kept the tissue alive, but it completely destroyed the lung's ability to clean itself. The adaptation solved one problem, but engineered a massive new one.
It's a heavy trade-off.
Now, I have to admit, I am a bit confused here. If a cell is mutating its identity like that, isn't that just cancer? I constantly hear the words dysplasia and metaplasia thrown around together.
This raises an important question, and it is a distinction we must be absolutely clear on. Metaplasia and dysplasia are profoundly different things. Metaplasia is orderly, controlled, and reversible. If a smoker quits smoking, the stem cells will eventually realize the stress is gone and slowly replace the tough squamous cells back with the normal ciliated cells.
So I go back to normal.
Yes, one normal cell type is just subbing in for another normal cell type. Dysplasia, however, means disordered, atypical, chaotic growth. The cells look abnormal under a microscope, the nuclei are enlarged, and they are not organizing properly. Dysplasia is premalignant.
So metaplasia is an organized remodeling project, and dysplasia is when the construction workers lose their blueprints, go totally rogue, and start building walls at random angles.
Precisely. But here is the tragic paradox of metaplasia. While the metaplasia itself is not cancer and is not even dysplasia, it creates a dangerous long-term vulnerability.
Because it's constantly changing.
Because by forcing the tissue to constantly reprogram and divide in a highly inflammatory environment, you drastically increase the statistical chance of a genetic error occurring. That is why patients with Barrett's esophagus have a significantly higher risk of that tissue eventually slipping into dysplasia and ultimately progressing to esophageal adenocarcinoma.
The shape-shifting keeps you alive today, but it puts you on a much riskier path for tomorrow.
It is a gamble the body is forced to take.
So what does this all mean? We have journeyed from 19th century pathology to Cold War nuclear fallout, spaceflight microgravity, and shape-shifting lung tissue. Why should you, the listener, care about the mechanics of cellular adaptation?
Because this microscopic world is the absolute foundation of your everyday health and modern medicine. This is not abstract textbook trivia.
That's happening right now.
Yes. When an aging man goes to the doctor for urinary issues, it is often due to benign prostatic hyperplasia cells multiplying in response to hormonal changes. When your primary care physician orders an echocardiogram to check your heart, they're specifically looking to see if your cells have chosen the dangerous calcineurin pathway in response to your blood pressure.
And when a patient is recovering in the ICU, the physical therapists are fighting a daily molecular war against the ubiquitin proteasome pathway, trying to stop muscle atrophy from bed rest.
Exactly.
And when a gastroenterologist performs a routine endoscopy, they are hunting for the metaplasia of Barrett's esophagus so they can intervene before the cellular construction workers go rogue and cause cancer.
Your cells are performing an invisible, highly regulated balancing act every single second of your life. They are constantly sensing the friction of your environment, down-regulating, up-regulating, and reshaping their architecture to keep you functioning.
It is a relentless fight for equilibrium. And as we wrap up this deep dive, there is one final provocative concept hidden in the sources that we want to leave you with. It is a fundamental biological principle called hormesis.
Ah, hormesis. It is the concept that a low dose of a physical or chemical stressor triggers a highly beneficial adaptive response.
Like lifting weights to build stronger muscles.
Or exposing yourself to a sauna to trigger heat shock proteins. But a high dose of that exact same stressor overwhelms the adaptation and triggers irreversible injury. The poison and the cure is entirely in the dose.
The poison is in the dose. So we want you to think about the physical or environmental stressors you are putting your own body through right now. Think about your workout routine, your sleep schedule, your diet, or even that chronic lingering ache you've been ignoring for months.
Pay attention to the dose.
Exactly. At what exact microscopic moment does your stress stop acting as a biological training mechanism and start pushing your cells past their amazing ability to adapt right to the edge of injury? Because as we have learned today, your cells are doing everything in their power to save you, but ultimately you are the one controlling the dose.